Hello, everyone. My name is Abdalla, and today I'm going to present to you part of my research titled Copper oxide tungsten trioxide bimetallic oxygen carriers for chemical looping with oxygen uncoupling and chemical looping combustion. This work was done at the University of Calgary under the supervision of Professor Nader Mehempe and with collaboration of Dr. Muhammad Ali. My presentation will include an introduction about the CuO process, followed by literature review, and then we'll go through the materials and methods used in this research, followed by reactivity testing, materials characterization, and then we'll go through conclusions and future work. So from the increasing adverse effect of the global warming in the climate change, it's becoming more important to capture more CO2. And the technologies that are used for capturing CO2 can be categorized into post-combustion technologies, in which the CO2 is captured after combustion takes place. And there is a pre-combustion technologies in which the fuel will undergo a pre-treatment before combustion. And there is oxy-fuel combustion technologies in which the fuel is combusted in an oxygen-rich environment in order to produce mainly a flue gas stream that consists of CO2 and H2O that can be easily separated by simple condensation. Chemical looping combustion can be considered to be categorized with the oxy-fuel combustion technologies. However, the oxygen in this process is provided through the use of an oxygen carrier or solid material called oxygen carrier, which is typically a metal oxide supported over an inert material. And this oxygen carrier can be circulated between an air reactor and the fuel reactor. And by doing this circulation, we avoid the direct contact of air with nitrogen in air, and hence the NOx compounds will be immensely reduced during combustion. So the main components of the CLC are the fuel, the reactors, and the oxygen carriers. And we focus our research here on the oxygen carriers because their development will lead to a huge step towards the commercialization of the CLC process. So generally, CLC processes for solid fuels are being categorized into in situ gasification CLC or IGCLC and chemical looping with oxygen uncoupling or CuO. So in situ gasification CLC, IGCLC, steam or CO2 is being used as gasifying agents, and the gasification products are then react with the oxygen carriers. So the possible reactions for IGCLC after the transformation of coal into volatile matter and char, the char will be gasified with either steam or CO2 in order to produce CO or carbon monoxide and hydrogen. The carbon monoxide and hydrogen and the volatile matter will react with the oxygen carrier to produce CO2 and H2O, or more hydrogen can also be produced. For the CuO, the chemical looping with oxygen uncoupling, the mechanism is different. In this process, the oxygen is generated by the oxygen carrier directly, and then the gaseous oxygen will react with the char or the volatile matter. So for this process, the gasification step is not needed and faster combustion can be attained. Also, it's more efficient since we do not require to use any steam, which will also affect the economics of this process. So the possible reaction in the fuel reactor of the CuO process will be the generation of the oxygen from the oxygen carrier, and then the char will be reacting with the gaseous oxygen, and also the volatile matter, carbon monoxide and hydrogen will be reacting with the gaseous oxygen in order to produce CO2 and H2O. In this process, the oxygen carrying capacity have a huge effect on the solids inventory or the amount of the oxygen carriers that are being circulated from the air reactor and the fuel reactor. So here I will be presenting a brief literature review. In this literature review, we have found that the oxygen carriers properties are really important in order to satisfy the requirements for the CLC process or the CuO process. And these properties required in the oxygen carriers include high reactivity and high resistance to sintering, since the reaction temperatures are high. And it was found that the copper-based oxygen carriers are among the most attractive materials for CuO, and this is because of their characteristics of an ability to generate oxygen at the required reaction temperatures. In a paper done by Adenes group, it was found that copper oxide with 40% metal loading over zirconia was identified to be one of the most suitable oxygen carriers for CuO, and they have used different metallic oxygen carriers and different supports and different loadings, and this oxygen carrier was among the most appropriate for CuO. Also, in other papers, we have found that combined oxygen carriers have been used in order to improve the performance of the oxygen carriers. For example, copper with manganese or copper, manganese, and iron were used for CuO, and they have shown very improved reactivity and stability and very high CO2 capture efficiencies. However, tungsten was not studied before for CuO, and the tungsten have very attractive properties, very high melting point, and very attractive structural and thermochemical properties. However, when it's used on its own, it does not provide very high CuO reactivity. However, in this work, it's suggested to be used as a second or a combined oxygen carrier together with copper and to be investigated for CuO when supported over zirconia. So in order to investigate the effect of the addition of the tungsten oxide to copper, we have firstly prepared a copper oxide over zirconia and using impregnation method. And in this synthesis method, we have used the precursor of copper together with the support and have been mixed in water for 6 hours, followed by evaporation of the water and then drying at 120 degrees Celsius for 12 hours, followed by calcination at 800 degrees Celsius for 8 hours before we get our final oxygen carrier. Similarly, we have prepared a mixed metal oxide using the co-impregnation method. With the co-impregnation method, we mean we have mixed both the precursors of both tungsten oxide or both tungsten and copper at the same time in water, and the same procedure was followed. And final nominal loadings were 40% for copper oxide and 20% for tungsten trioxide over zirconia. And we named this sample as the co-impregnated sample. In order to investigate the effect of the sequence or the addition of the tungsten trioxide to the oxygen carrier, we have also prepared another sample and we have named it the sequential impregnated sample. And in this sample, we have done 2 steps of impregnation. Firstly, we have impregnated tungsten trioxide over zirconia, and we have used this material as a support that we impregnated the copper oxide on in the second step. So we aim to have the same nominal loadings as the co-impregnated sample, and we named this sample as a sequential impregnated sample. In order to see the different effects of the different synthesis method or the addition of the tungsten trioxide, we have tested our samples for the CuO testing and the oxygen release, and we have used a TGA for that using reduction gas or inert environment as nitrogen at 1000 degrees Celsius. And in order to reoxidize the sample, we used air at 800 degrees Celsius, and the oxidation step generally requires lower temperatures than the reduction step. We have performed 10 cycles in the TGA, and the results are shown in the left-hand side here. And we see in gray is the performance of the tungsten trioxide over zirconia, and this sample did not show any CuO reactivity for the 10 cycles of the CuO cycles. However, for the base material of the single metal oxide, copper oxide over zirconia, shown in orange here, it showed an average CuO transport capacity of 4.17%, and the mixed oxygen carriers have shown higher oxygen transport capacity or average oxygen transport capacity, with the sequential impregnated sample showing around 4.45%, while the co-impregnated sample showed a very high oxygen transport capacity compared with the other samples of 6.6% oxygen transport capacity. We'll go into further discussion of these results in a later slide. However, we have performed some characterizations in order to understand how we got these different performances from the different samples, and we started using the XRD of the samples, the oxidized samples, and after reduction. So we've used a fixed bed reactor in order to reduce the samples using the same conditions that are used in TGA, and then we took the sample out and tested them for XRD. So the support in all samples have exhibited the body light phase for all the samples, either oxidized or reduced. And for the copper-based sample, the oxidized sample have shown a tenorite phase, which is a copper oxide phase, CuO, together with the support or the zirconia phase. However, for the tungsten-based sample, it showed a tungsten trioxide phase together with the zirconia phase. The co-impregnated sample have showed some interaction between the active metals. However, there was no interaction with the support. And the active metals, the copper and tungsten, showed some interaction, and they formed some intermediate phase, copper tungsten oxide phase, CuO3 WO6, that was rich in copper. However, the sequentially impregnated sample showed an intermediate phase that has less copper in it, which is CuWO4, which is known to be an oxygen deficient phase. For the reduced phases, for the copper-based sample, it showed a cuprite phase, which is CuO2O, and this phase is known to be the reduced phase in the CuO process. However, the tungsten trioxide or the tungsten-based sample did not show any change between the oxidized and the reduced sample, and this was also confirmed from the TGA that it did not show any reduction for the conditions used. However, the co-impregnated sample has showed the support phase together with the CuO2O phase and also some intermediate phase that is CuO2WO4. The same phase was also present for the sequentially impregnated sample, and we'll go through the suggested mechanisms that resulted in both samples having the same characteristic peaks for XRD at the end for the reduced materials. We have performed SEM EDS analysis for the co-impregnated sample, and we found that the tungsten was not always present on its own. However, it was present always with the copper in the material. And this confirms that we have the intermediate phase that we got in the XRD analysis. Also, this material has a more compact and round structure, and this will provide more surface area for oxygen release. And this is why we had a higher oxygen release in the TGA results for the CuO testing. For the sequential impregnated sample, we had similar results in which the copper and tungsten were always present together. The tungsten was not present on its own. And also, this structure have more elongated structure and larger crystallites. This was also confirmed from the Scherer equation calculations from the XRD results. This sample have a higher crystallite sizes, which means that we have less surface area for oxygen release. And this is why it was lower than the co-impregnated sample in the oxygen release for the CuO testing. We have also performed hydrogen temperature program reduction or hydrogen TPR in order to study the redox properties of the different materials used. We see that in the left-hand side, the TPR profiles for the tungsten-based over zirconia, it showed very high temperatures for reduction. It started almost at 700 degrees Celsius, while the copper-based sample, it's easily reducible and can start at 200 degrees Celsius to 400 degrees Celsius. The mixed oxygen carriers have shown intermediate reduction temperatures, and this confirms that the intermediate phases will help with the reduction of the tungsten trioxide. And this is why we have some intermediate reduction temperatures for both the mixed metal oxides. We have also analyzed the quantitative hydrogen consumption on the right-hand side in this slide. And the co-impregnated sample showed the highest hydrogen consumption among the other samples. And this gives an indication about the amount of oxygen available in the material. And this goes in line with the results that we got in the CuO testing. This table here we got also from the TGA results. And we see in the first column, we have the CuO oxygen transport capacity for the samples, average for 10 cycles. And we see that the first sample or the single metal oxide sample showed 4.17% oxygen transport capacity, while both mixed oxides have shown higher oxygen transport capacities. And this was attributed to the presence of the intermediate phases that led to better reduction of the tungsten trioxide phase. So the co-impregnated phase showed the highest oxygen transport capacity due to the formation of different intermediate phases on this sample when we compare it with the sequential impregnated sample. So the second and the third column shows the rate indices for both reduction and oxidation. And we see for the single metal oxide, it showed the highest or the fastest kinetics when we compare it with the other samples. This was also known in literature because with the formation of the intermediate phases, the reduction will be slower and will be compromising the kinetics of the samples. However, we did not drastically compromise the kinetics for the co-impregnated sample, and we have some intermediate kinetics when we compare it with the sequential impregnated sample. So depending on the results above, we have suggested redox mechanisms for the three samples, depending on the XRD, TPR, and the TGA results. And for the single metal oxide, the CuO was transformed into CuO, and this is well known in literature. For the co-impregnated samples, we have some free CuO. it was suggested to be reduced into CuO, and during synthesis, we formed the intermediate Cu3WO6 intermediate phase that was reduced to Cu2WO4 together with generation of oxygen. For the sequential impregnated sample, similar reaction to the single metal oxide was occurring together with the formation of CuWO4 during synthesis, and this phase requires some CuO in order to react with, in order to produce the Cu2WO4 that was present in the reduced XRD peaks, together with the formation of oxygen. And this reaction on the sequential impregnated sample is expected to be slow, and this is why we have slower kinetics for this sample when we compare it with the compregnated sample. So as a conclusion, we added the tungsten trioxide to CuO over zirconia through either co-impregnation or sequential impregnation. Both mixed metal oxide showed higher oxygen transport capacity when we compared with the single metal oxide, and this is due to formation of intermediate phases, easing the reduction of the tungsten trioxide. Also, the co-impregnated sample showed higher oxygen transport capacity and faster kinetics when we compared the sequential impregnated sample, and this is due to the formation of the Cu3WO6 intermediate phase that is rich in copper, and this sample has more compact structure and smaller crystallite size when we compare to the other sample, and this will lead to higher surface area, allowing more oxygen release from this sample. Also, the suggested redox mechanism for this sample is different from the sequentially impregnated sample, and this will lead to different kinetics on the different samples. So as a future work, it's recommended that to use in situ XRD characterization technique in order to confirm the redox mechanism of the oxygen carriers, and also to test our samples on a CuO unit in order to investigate the oxygen carriers' mechanical properties, and also to test these materials with different fuels, and to test for CL, for example, or IG cells. At the end, I would like to acknowledge the support that I got from the CuO School of Engineering at the University of Calgary and the financial support I got from the Canadian Natural Resources Limited through MITABs. These are the references that I used for this presentation. And thank you so much.